Now, as we move in to our example 3, I'm going to talk about symmetry a little bit. Symmetry with polar graphs. I used that word earlier. Symmetry means that like you could cut it in half and it's a mirror image on either side. There are 3 types of symmetry. I don't know if you remember, there were 3 types of symmetry. You could have symmetry with regard to the y-axis, symmetry with regard to the x-axis, and if it's not the y-axis, which means left to right, or x-axis, top to bottom, it would be diagonal. Do you remember what we called that? The origin. Symmetry with respect to the origin. Okay, so how does it play out with polar? Well, let me show you by using visuals. I'm going to use an x and y axis. I think it's just easier to see. Truthfully, I should be using circular graphs, but I'm going to show it to you this way. Visually, if a graph r theta, normally for r theta, where do we normally begin with theta? Not to the origin, sorry. We begin on a polar graph. I know that I drew x and y. We usually begin to which side? Up, down, on the circle. Where do you usually begin in a circle?
The right.
To the right. Usually we begin to the right and we move like a clock or against the clock? Against the clock, this way. That's what we normally do for a graph of r comma theta. That's normal. What this says, what if you had a value that produced the same values with this math? Okay, this is saying you have an r value. This says begin at pi, but move against the clock. Where is pi? The left. So we have the same r value. So whatever this distance is away, you begin the same spot. But this time I begin at pi. So if this one began at 0, this time I'm beginning at pi and I move against the clock. Let me do the opposite color. Let me do this in green. I begin here and I move against the clock. What type of symmetry is this? Is it symmetry with regard to the x-axis, y-axis, or the origin? This is the y-axis. If this case is true, you have symmetry with regard to the y-axis. And in polar terms, they don't call it symmetry with respect to the y-axis. They would give it by the theta. Y is the same thing as a theta of how much? Pi over 2. Theta equals pi over 2. Okay, that right there, both of these 2 cases mean the same thing. You could write it this way, r pi minus theta, or because that means you still have the same r value. That means the same distance away from the origin, same distance. Start at pi, move like a clock. Or this one says you start at the same location, but instead of moving up, you go down, and as you go down, your r is opposite, so you're straight across. So you start here, start across, go over there. So it's the same concept, negative r comma negative theta, and negative theta moves against the clock going this way, but since it's a negative r, it rotates it over. So it's actually the same exact graph. So same graph for both situations. All right, next one. Draw another graph. Let's get the standard. Normally, we begin on the right side and we move against the clock. Normally, we begin on the right side and we move against the clock like that. That's normal, r comma theta. Now this says you still have the same r value, which means the same distance away from the pole, but you move with the clock. So this one's saying move with the clock. So instead of starting there and moving that way, go this direction. This is when you have r comma negative theta, or that case, which I'm running out of space. It's the same thing. Negative r comma pi minus theta. Okay. For these, what type of symmetry is that? Symmetry with the x-axis or the y-axis? Or the origin? It's with the x. That's right. I'm going to go ahead and erase that. It's just too much going on. So symmetry with the x-axis in polar, what they call that, if you have symmetry with the x-axis, is they call that symmetry with respect to the polar axis. That's what they call the x-axis, is the polar axis. Finally, last type of symmetry, you could guess it from earlier this year. If it's not symmetry with the x-axis and not symmetry with the y-axis, but still symmetric, we'd say it's symmetric with the origin. This one's going to be with the origin. So you're going to start on the right, curve it up visually. That's r comma theta. What this is saying is you can start with the same theta and move this way, but instead of having a positive r, it's a negative r, which means it's across and going this direction. So this time, if it looks like this, if your symmetry is going like that, that means you are symmetric with the origin. The other way of writing this is starting at pi, but continuing to move against the clock. Both of those would give you that. That's symmetric with regard in respect to the origin there. So in polar, they don't call it an origin. Does anybody remember what they call it? I've said it a few times today. The pole. You won't have to write B twice. It says symmetric with respect to the pole. There you go. It says these three tests are sufficient to guarantee symmetry, but failing a test does not guarantee the graph does not appear symmetric. Sine. Sine is what letter again? Sine is y. Sine will always have respect to the y-axis, which in polar, what is another name for the y-axis in polar? Theta equals pi over 2. Perfect. And cosine. Cosine is what letter? X. Therefore, it would have any cosine graph will have symmetry with the x-axis, also known as the polar axis. I'm running out of space. Polar axis. There you go. That's symmetry.